So right now we're going to be solving a kinematics problem. The problem is, at time equals 0 seconds, a car has a speed of 30 meters per second. After 6 seconds, its speed is 15 meters per second. There are three things we're going to need to do. We're going to need to graph the situation on a velocity versus time graph. Then we'll use that velocity versus time graph to figure out the average acceleration of the car, before finally figuring out how far it travels in this time. So the first thing I'm going to do is graph it. Now, when I graphed it here, I knew that my time range, my x-axis, went from 0 to 6. On a graph, I would always recommend starting off with your value of 0, with whatever it is, so you can actually see the full range of data. So I'm starting off with 0 seconds here. My maximum time was 6, so I placed that at my very maximum grid. Now there are 10 boxes horizontally, so I took that maximum value, divided by 6, and that was my nice even scale. Now, I did the same thing vertically. I always start off at 0, and then my maximum y-axis value was the 30 meters per second, which is up here. And then 30 divided by the 10 boxes is a scale of 3 meters per second for each box, working my way up. Now, I ended up plotting those two data points I was given. 0 seconds, 30 meters per second up here. And then 6 seconds, 15 meters per second up here. And then I'm assuming it's uniform acceleration, so that means a constant slope on a VT graph, which is why I just drew a straight line connecting the dots. That's what I did when I graphed the situation. Now there's this whole blank area underneath here, but this way, if I did have a little vertical scale break from 0 to 15, someone that's not actually looking at the scale of the graph might think that the object came to a stop. That's why I did want to have it start off from a velocity of 0, so that way we can see even after 6 seconds, this object is still moving pretty quickly. So, next thing we're going to be doing is figuring out the average acceleration of the car. Now, figuring out acceleration from a VT graph is super easy. The slope of a velocity versus time graph is the acceleration. So, I do y2 minus y1 over x2 minus x1, but I make it physics appropriate. So my y-axis is my velocities, so I figure out my change in velocities. And then I divide that by my x-axis, which is my times. So I divide by my change in times. So my second my second vertical point was 15. My first was 30, which is why it's 15 meters per second minus 30 meters per second. And then for my x-axis values, that's run. 6 minus 0. So acceleration will be negative 15 meters per second over 6 seconds. When I simplify that so that way I have a base 1, my acceleration would then be negative 2.5 meters per second each second, or negative 2.5 meters per square second. So then I can use one of my kinematic equations to figure out how far does it travel in this time. So I'm going to be using that equation we figured out by looking actually at the area under the curve on a VT graph and then algebraically rearranging it. It's the position is equal to our starting position plus our starting velocity times time plus 1/2 times the acceleration times time squared. Now I'm making an assumption that it starts off at a position of 0 meters plus the starting velocity of 30 meters per second times the time traveled, 6 seconds, plus 1/2 times the acceleration we calculated, negative 2.5 meters per square second, times the time, 6 seconds, squared. Then I solved in each of these terms. So when I did the 0 meters, plus 30 times 6, which is 180 meters, plus 1/2 times negative 2.5 times 6 squared, gives me negative 45. When I sum up all of those numbers, I end up saying that this car traveled 135 meters during those 6 seconds. This is one way to figure out how far it went, by using a kinematic equation. Another way is by using the area under the curve on a velocity versus time graph, which tells us the change in position, or the distance traveled. So, in this region, I'm treating it just like we did with our VT graph from the Grant Lab. I'm breaking up into two shapes we know, a rectangle and a triangle. I calculate the area of each of those two regions, and then I add them together. And then you'll notice that when we check the math, I end up with the exact same value as though I were solving it with just a pure-on kinematic equation without having to deal with the graph. We have multiple ways of arriving at the same answer. It just depends on how you'd like to approach the problem.